Let's see the simple way to check transitive closure of given relation R. So in this first we have to represent the relation using the matrix. So you know that how to represent a given relation into the matrix. So in this case relation is on set A and set A containing the 4 elements. So we required 4 by 4 matrix. So here I taken 4 by 4 matrix. So write down 1, 2, 3, 4 and at a row side and 1, 2, 3, 4 at column side. If that particular order pair is present in the relation, then its entry will be marked as a 1 in the matrix. If that order pair is not present, then its entry will be marked as a 0 in the matrix. So using this, you can see that in given relation order pair presents are 1, 2, so mark it as 1. 2, 3 is present, so it also mark as 1. 2, 1 is present. 3, 4 is also present. So all this entry will be appear as a 1 and other entries is marked as a zeros. Now using this matrix we have to find which are the missing order pair for to become a given relation as a transitive relation. So for this there is a trick. You have to take in this case there are 4 by 4 matrix. So take a 4 columns and 2 rows. First row is for column and second row is for the rows. So in this case 1 by 1. So initially consider first column of the matrix and first row of the matrix. In that check where the entries of the matrix is 1. So in column number 1 you can check second entry is 1, so write down here 2. Then there is no other entry as a 1. Then check the rows of the matrix. So in rows of the matrix you will get 1 at the second entry, so write down it as a second. Then in second column take a second column and second rows of the given matrix or obtained matrix. So you will find out entries at column at the first as a 1. In case of rows you will get one entry at 1 and third position. So take it as a second set 1, 3. In third column, for third column take a third column and third rows. Check in third column one entry will be appear in second position, so write down here 2. Then in third row you will get entry 1 at the fourth position, so write down here 4. In the same way for the 4 column you will get a entry of one entry at the third position in column, and there is no one in the row, fourth row, so mark it as a 5 or 0. Now take a Cartesian product of this column and row. You will get order pair. So in this case, in number 1 column 2, 2 pair will be you will get a 2, 2 pair. Then in second column you will get 1, 1 and 1, 3 pair. In third column you will get 2, 4 pair, and here as a second element is a 5, so it will give the Cartesian product as a 5, because for Cartesian product condition is that both sets should be non-empty set. So here it is empty, so Cartesian product will be 0. After this you can check that which pair is present in the relation and which is not present in the relation R. So whatever the pair which are missed in the relation R, that pairs we will add from this resultant Cartesian product pairs. So transitive closure of relation R will be as given below. So R is equal to 1, 2, 2, 3, 3, 4, 2, 1, 2, 2, 1, 1, 1, 3 and 2, 4. So if you check, this will satisfy the properties of transitive. That's why this relation is a transitive relation. You can check here 1 comma 2 is there, 2 comma 3 is there. For that 1 comma 3 should be in the relation R, so it is present. 1 comma 2, 2 comma 1, so 1 comma pair should be present, it is present here. Then 1 comma 2, 2 comma 4, so 1 comma 4 pair should be present in the relation. So this pair is also present. Due to newly added pair, we have to again check whether the transitive relation is exist or not. So if not exist, then again we have to apply this. Then you will, at the end, you will get a transitive relation, and minimal transitive relation is called as a transitive closure of this given relation R. Now we have one more way to find out the transitive relation or transitive closure of the given relation. It is by Warshall algorithm. So in this algorithm, we are representing the given relation by the matrix, and simultaneously we also representing this relation by the digraph. And we have to apply these steps. We will calculate the matrices W0, W1 up to Wn, where Mr is equal to W0, Wk is given by Wij k, where Wij k is equal to 1 if there exists a path from vertex I to j in the corresponding digraph such that all the intermediate vertices of this path are in the set 1, 2, k or 0 otherwise. So we'll see the relation R is given relation. So these are the order pair exist, that is 1 comma 3, then 2 comma 1, then 2 comma 4 and 4 comma 2. These are the existing order pair in the relation, and you want to make you want to find the transitive closure of this given relation. So it is also represented in digraph. So if there is a order pair from 1 to 3, then we know that how to represent it. So 1 to 3 edge is shown in this diagram. In the same way 2 to 1 and 4 to 2 and 2 to 4 edges are shown. Now from this matrix, so R1 will be found. In case of R1 will be treated as a middle node, and from this node we have to find out the other edges. So this 1 edge is incoming edge to the towards the 1 vertex, and this is outgoing edge from 1 to 3, so it is middle one for this 2. So 2 is related with 1, 1 is related with 3, therefore 2 is also related with 3. So this one order pair is added in the R1. So this is modified matrix or modified relation. After that, this relation will be taken as an input for the R2. In case of R2, we will not doing any changes in this 2. So here we can see that 2 will be taken as a middle node. As it is created as a middle node, we will check incoming and outgoing edges from the 2. So in this case, incoming edge is 4 to 2 and outgoing edge is 2 to 1, and because of these 2 edges, 4 is related with 2, 2 is related with 1, therefore 4 should be related with 1. This edge is added. Then this 4 is related with 2 and 2 is related with 4. For this pair, 4 should be related with 4, therefore this self edge is added. Then 4 is related with 2 and 2 is related with 3, therefore this 4 is related with 3 edge is also added. So these 3 new order pairs will be added in this R2 matrix. So take this as an input for the next iteration. So here R3 will be calculated. In this case 3 is considered as a middle edge. So we will see incoming and outgoing edges for this. There are only incoming edges, so there is no way to add a new edge due to transitive property. So this matrix will remain as it is. Then same matrix will be taken as an input for the R4. In case of R4, 4 is treated as a middle one. So we will check transitive property is established or not. So 4 is related with 2 and 2 is related with 4. So 4 comma 4 is already added in the matrix. Again 2 is related with 4 and 4 is related with 2. That's why 2 comma 2 pair should be in the relation, so that order pair is added. So there is no any other edges as per the transitive property. So this will be the final result, and this is the transitive closure of the given relation R by the Warshall algorithm. After that, next concept is that partial order relation. A relation R on set S is called a partial ordering or partial order if it is reflexive, antisymmetric and transitive. Means whatever the given relation on set S, if it's satisfying reflexive property, antisymmetric property and transitive property, then it is called as a partial order relation. You know that what is meant by reflexive property, what is meant by antisymmetric property and transitive property. So whatever the given relation, you have to check if these three properties are satisfying, then we can declare that relation as a partial order relation. The set S together with the partial ordering R is called a partially ordered set or poset and denoted by S comma R. A partial order R is also denoted as lesser than equal to. This is the notation for partial order or poset. The elements A and B of a poset S comma less than equal to are called comparable if either A lesser than equal to B or B lesser than equal to A. Otherwise A and B are called incomparable. If S lesser than equal to is a partial ordering set and every two elements of S are comparable, S is called a totally ordered or linearly ordered set. A totally ordered set is called a chain, and totally, if it is not totally ordered, then it is called as an anti-chain. We will see some example on this partial order relation.